This lesson is about higher order derivative of a function. At the end of this lesson, you must be able to determine the higher order derivatives of a given function. In the past lessons, we had been working on the derivative of y with respect to x. And if the function f is a differentiable function, then its derivative f prime is itself a function and may be differentiable. Hence, when you differentiate f prime with respect to x, then you get what we call the second derivative of f with respect to x, denoted by f double prime. And that, for as long as the resulting derivative functions are differentiable, then we can continue the process of differentiating the said function to obtain much higher derivatives. Here are the common notations used for higher derivatives of y with respect to x. That given the function y is a function of x, then the first derivative defined by dy dx can be denoted by making use of any one of these symbols. So we have dy dx, or we have y prime, or it can be given in terms of f prime of x, or the derivative of f of x with respect to x, or in terms of the differential operator capital D, the derivative of f of x with respect to x. The second derivative of y with respect to x is denoted with the symbol d squared y dx squared, read as the second derivative of y twice with respect to x. And this is defined simply in terms of the derivative with respect to x of the first derivative of y with respect to x. Okay, so the other notations for the second derivative are as given here. So we have y double prime, f double prime of x, or we have second derivative of f of x twice with respect to x, or using the differential operator capital D, and we have here the second derivative of f of x with respect to x. In general, we can define the nth derivative of the function y equal to f of x, and that the nth derivative of y with respect to x is just the derivative with respect to x of the n minus 1 derivative of y with respect to x. Okay, and the other notations are as given. So you have y to the n. This is not an exponent. This would denote nth derivative of y, or the nth derivative of f of x. Okay, or in terms of the differential operator, is still to mean nth derivative of f of x with respect to x. We mentioned last time that we credit Leibniz to some symbols or notations that we use in differential calculus. So this symbol of dy dx, d squared y dx squared, or in general dny dx to the n, which would denote nth derivative of y with respect to x, are all called Leibniz notations. In this example, we would like to find all the non-zero higher derivatives of the function y is equal to 3x to the 6 minus 4 x to the 4th plus 5x cubed minus 6x squared plus 7x minus 8. In differentiating this expression, we will be applying this rule for differentiation of a power of x, where the derivative with respect to x of a constant c times x to the n is given by c times n times x to the n minus 1. Recall that the derivative of a constant is just equal to 0. So applying these rules now, differentiating on the function y, we obtain y prime equal to 18x to the 5th minus 16x cubed plus 15x squared minus 12x plus 7. The second derivative is obtained by differentiating the first derivative with respect to x. So for the first term, we will have 18 times 5 times x to the 4th, thus giving us a 90x to the 4th. Second term will be negative 48x squared followed by positive 30x minus 12. Again, applying these rules. The third derivative would just be the derivative of the second derivative with respect to x, resulting to a 360x cubed minus 96x plus 30. And since this is not due to 0, we continue and work on the fourth derivative of y with respect to x, differentiating the third derivative. And the derivative of this thing with respect to x would just be 1080x squared minus 96. And on that basis, work on the fifth derivative to be given by 2160x. And the sixth derivative, just a constant, equal to 2160. Now, since this is already a constant, and knowing that the derivative of a constant is 0, then the non-zero higher derivatives of this particular function would go only up to the sixth derivative. For our second example, we would like to determine the second derivative of y with respect to x given the function y is equal to 2x divided by 2 minus 3x. For our solution, let us take note that y is a ratio of two functions. And recall that when you differentiate a ratio of f to g, the derivative would just be equal to the denominator g times the derivative of the numerator minus the numerator f times the derivative of the denominator g. This difference to be divided by the square of the denominator. So when this differentiation rule is applied to differentiate the given function y equal to 2x divided by 2 minus 3x, then the first derivative will be given as follows. We have 2 minus 3x, which is the denominator, times the derivative of 2x, which is just a 2, minus the product of the numerator 2x with the derivative of 2 minus 3x, which is just a negative 3. This difference to be divided by the square of the denominator 2 minus 3x. Okay, so what we do next is to simplify the numerator. We multiply these factors together and then combine similar terms so that the numerator now would be given by 4 minus 3x plus 6x. And simplifying the numerator, combining similar terms, then that would just give us a 4 to be divided by the square of 2 minus 3x. Having this as our first derivative, since the requirement is the second derivative of y with respect to x, then what we do is to differentiate the first derivative dy dx with respect to x again. Okay, so we now differentiate the first derivative. Again, note that we have here a fraction, so again we can make use of this rule and come up with the derivative expressed as follows. So this is the denominator times the derivative of the numerator 4, which is just giving us a derivative of 0, then minus 4 times the derivative of the square of 2 minus 3x. Using the rule differentiating a general power, u to the n, the derivative is n, u to the n minus 1 times du dx. Hence, the derivative of 2 minus 3x squared would just be a 2 times 2 minus 3x raised to the first power times the derivative of 2 minus 3x, which is a negative 3. This difference now is to be divided by the square of the denominator. Hence, we have there a 2 minus 3x raised to the fourth power. Okay? Or, the second derivative of y with respect to x would just be equal to this ratio of the product of 24 with 2 minus 3x to the fourth power of 2 minus 3x. Now, take note that 2 minus 3x is a common factor of the numerator and the denominator. Hence, the second derivative of y with respect to x would just be given by the ratio of 24 to the cube of 2 minus 3x. To recap the discussion, a differentiable function y is equal to f of x when differentiated with respect to the independent variable x will result to the first order derivative of y with respect to x. Now this resulting function may be differentiable as well, hence can be differentiated again with respect to x, resulting to the second order derivative of y with respect to x. In general, the nth order derivative of a function is determined by differentiating with respect to the independent variable x the n minus 1 derivative of the said function.